It's a great honor to introduce Shash. Shash was an IBM intern, research intern last summer, and he's working on quite a few things. For example, he's working on cybersecurity. He's working on programming language, and in the last summer, we are working on adversarial attacks for computer programs. And I guess today, Shash will present his ICLEA work on adversarial attacks models for computer programs. So, no talk. Thanks.
Thank you, Sergio, for the introduction. Hi, everyone. I'm Shash. I'm a graduate student in the Department of Electrical Engineering and Computer Science at MIT, where I'm advised by Unime O'Reilly, who heads the Alpha Lab at CSAIL, which is the computer science department. And yeah, I'll be talking about adversarial attacks on computer programs. Broadly, my interests are at the intersection of machine learning, programming languages / software engineering, and cognitive neuroscience. So I'm trying to build a picture which connects all these three as part of my larger thesis. All right, this work is a result of a very fruitful collaboration between MIT-IBM AI Lab and CSAIL, where Sergio and Unime had a joint proposal on some of the themes that I'll be talking about in this work. So thank you all to my excellent collaborators on this work. Also, as Sergio mentioned, I did most of this work as part of an internship last summer, which was when the world seemed to be coming to an end. So yeah, thank you, Sergio and David, for having me over. It was a great experience. I had a ball of a time. Yeah. Also, Tamara, who's mentioned here, she's an undergraduate at MIT in her in her junior year now. And this was her first big research project, so that she was involved in. So cheers to her, and I'm glad that she could contribute, and it was great having her on the team as well. All right, so let me begin by introducing you all to this interesting world of machine learning for PL / software engineering tasks. PL is programming languages. So over the last, I would say, 5 to 6 years, this field has started gaining momentum, where almost all the top conferences at the intersection of these two fields of either machine learning or software engineering and programming languages, you would see some workshop or the other snuck in, which has tried to address this issue. And a few interesting applications have come out of these efforts. Probably the most prominent of it is code auto-completion, where Eclipse and Visual Studio, these are two popular IDEs. In fact, as of today, I think both of these are shipped with this technology where, like Google, if you're writing something, given the context, it'll try to auto-complete it. Eclipse is a little more nerdy in the sense that it actually gives you some confidence intervals as well as to what is the most likely piece of code that will follow what you've written. So this has gained some popularity. A lot of money is being poured into it by groups like Microsoft and Visual Studio, where they're trying to productize this and making sure that the end user actually sees the benefit of all this work. That may perhaps be the poster boy application, but there are a couple more. So improving variable names. So this particular application came about in like 2014. Which was pretty much like the application which brought this entire space onto the map. So improving variable names, like as with any sort of JavaScript developer would know, I mean, these variable names are usually very difficult to understand what's going on in the program because of like very terse names being used. And what this application does is you give it a piece of code with those poorly named variables, and it infers what the most likely meaningful variable names would have been. So this has been like a success story for folks in the JavaScript world. Assignment, grading, error fixing, feedback. Again, all of these verticals have seen some progress or the other of machine learning helping these tools. And it's getting popular. It's being adopted by different universities, and they're trying it out in their settings to see how it works. Vulnerability detection and malware detection is also like a big field where ML has seen some impact. So I think there are 3 or 4 big works which have shown interesting results of using ML for these kinds of malware and vulnerability detections. I also know that there's a group within IBM research itself, which is very interested in this very specific problem of detecting vulnerabilities using ML technology. And yeah, there are some other technologies and some other examples. So right about the time when we were submitting this work, or probably a month before, this was a paper that was released on arXiv by a group from Cornell, which showed some of the shortcomings of these kinds of applications. So what they showed was in a cryptography library, in a fairly popular cryptography library implemented in Python, this auto-completion system can pretty much be rigged in order to prompt a library which is actually known to have some vulnerabilities. So AES is the protocol, cryptography protocol, and CBC is one such specification of that protocol, and which is known to have some vulnerabilities and issues in it. And they managed to rig this auto-completion module, which is available as a package in Vim, and showed that, okay, if you do type in this, it prompts with the highest probability the incorrect or the vulnerable library. So this is some areas where these kinds of technologies can go wrong. And what we in fact explore is a more systematic understanding of how this can go wrong. So the overall architecture, this shouldn't be new to folks over here. So broadly, you have a program, you represent it, you have a design choice of either representing it either as a stream of text or as a graph or tree or any such data structure. And they all have their pros and cons. You push them into a model, the model learns some distributed representation of your input, and you use that to learn your downstream task. Your downstream task being code auto completion or some such. So this is broadly the overall setup, and the specific setup that we explore in our work is the problem. We explore the problem of program summarization or function summarization. And how this game works is you're given a program, and the aim is for the model to come up with like a textual summary of what the program is trying to do. And concretely, how this is trained or how the system is learned is you pick those functions with meaningful function names, with the assumption that those function names are a good enough proxy or a good enough description of what is happening in the program. You mask it, push it into your model, and use this as your supervision. And that's how you train your model to learn a summary of a given function. So this has been a task which has been used by several other works over the last 2 or 3 years to benchmark various aspects of this entire line of work of ML4 code. And also Visual Studio seems to have integrated some of this technology into automatically creating.
A question?
Yeah, sure.
Sorry, this is language dependent, right?
This specifically is language dependent. Yeah, I mean, the model would be language dependent. So people have shown this for Java and Python and whatnot. So they've trained different models for different languages and have shown that it works pretty decently.
But not a common summary for several languages.
No,
okay.
no.
Okay.
So that line of work has not been explored. So
okay.
Language agnostic model has not yet been.
Okay, thanks.
Not in this specific task, but I know of other tasks where language agnostic work has been done. But yeah, not for this specific task.
Okay.
Right. So let me give you like a small use case of where our work, just to concretize the idea of where our work sits into this picture. And you may come back and argue several sort of shortcomings in this little sort of schematic that I'll lay out in front of you. And the point here is to just broadly give you a sense for what it is that we do and where it sits in the overall picture with respect to this task. However, the formulation that we propose and the methods that we propose are agnostic of any one particular task or a programming language or a model. So it doesn't really depend on any of them. So let's say you've got like Alice and Bob. Bob is a software engineer who writes code and pushes code to a repository. And Alice, who's Bob's manager, receives a report once a week just to see what Bob is up to. And the report essentially uses this learning technology of like trying to summarize the kinds of code Bob has pushed to the code repository. So it pulls out code from there, summarizes it, and gives a report saying, okay, these are the 5 things that Bob was up to this week. Now, Bob being malicious Bob, those are his horns, he wants to go ahead and trick the system into pushing code which actually does something nasty. He knows probably that the code review process is not strong enough or whatever. I mean, those are hypotheticals, but let's imagine Bob to want to push something called hijack database. So this is some malicious piece of code that he wants to push upstream. But he knows that probably it may go past it's so subtle and so nuanced that the reviewer who's reviewing his code may miss it. But this learning system is fairly good and actually would probably summarize the activity as hijack DB, and Alice would be like, okay, what the hell is Bob up to? So in order to avoid the situation, Bob could probably use this formulation that we propose and then say, okay, now what happens is, although he pushes hijack DB into the code base upstream, he modifies his code in such a way that it still functions like the original thing that he intended to, but the model conveniently sort of completely misses labeling it and instead recognizes it to be something benign like backing up DB or something. So when Alice looks at the report, she'll be like, okay, Bob has written some code to back up some DBs, which sounds fine. And that way, Bob has managed to push some malicious code upstream. So this is like the larger context to think about and ground your understanding of the things that I'll follow this up with. Yeah, happy to take any questions. So please feel free to interrupt. Yeah. All right. So the model, the problem right now is to perturb a program P in order to fool a downstream classifier. So that's really what we are after. And the hope is that if the models really learn intrinsic properties of these programs and they're not and they're as good as a human, it should be hard to fool such classifiers, but we don't know. So that's what we want to go ahead and test. So all the hype and all the progress that's happened over there, we just want to go ahead and evaluate for ourselves how good these models really are. So let me start with a primer on like adversarial robustness in the case of images. And this will help me motivate how we can think about this problem for programs. So with images, as most of you would know, so you have like an image and the classifier recognizes it correctly called Panda. And the goal is to learn a map which, when you add it to this image, still manages to look similar to a human expert or a human. But the model completely misses the contents of it and instead misclassifies it, in this case, calls it to be a gibbon. So we immediately recognize 2 constraints. One constraint is that it needs to be similar to a human, but then dissimilar to a model which is going through this image. The question is, what is the parallel? I mean, what's the right way to think about this entire problem in the space of programs? So what is it that we can learn and we can nicely add to this program such that the resultant satisfies the 2 properties that we spoke of? And since this is the realm of programs that we're dealing with, there's an additional constraint over here. So it not only does it have to look similar to a human, different to a machine, or like a model, a trained model, it also needs to look exactly the same. This is not similar. It needs to look exactly the same to a compiler which goes through this program, so that at the end of the day, the functioning of this program remains the same. That remains intact. So you're not messing around with the true semantics of it, the functioning of it. But then the question is, what can you do which satisfies all these 3 constraints at the same time? So here comes in program obfuscations. So obfuscations is something that has existed for the last, I don't know, 30, 40 years, or probably much more than that, since the beginning of programming itself, where in order to hide some, you can think of these programs to contain 2 components. One is a component which the machine interacts with and one which the human interacts with. And obfuscations are those kinds of transformations or operations that you can pretty much use to alter the human component aspect of it. So for instance, variable names are pretty much completely human components. It doesn't really matter whether you use X or Shash or whatever. It's just something that we read it's completely the same for like a machine. So what we identify, and a couple of words before, as I've said, tried spotting this and had begun spotting this, is that can we use these kinds of obfuscation operations? And can we learn some interesting obfuscations, or what is the best set of obfuscations, which, when added to this program, manages to tick all these requirements? So it manages to fool it, looks kind of similar under some definition for similar, and that's our threat model. But it looks exactly the same to a compiler when the compiler goes through the program. So functionally, it remains the same. So in this work, we explore a bunch of transformations, and the broad categories of these transformations are either replace. So we replace existing variable names, say, with some other variable names. So these are all, there's like a multiplicity of these variable names, and you can pick and choose whichever. You could use function parameters, which are again names at the end of the day, or you could insert stuff. So the inserting, again, is depending on your threat model, whether insertion works or not is totally up to you. But the nice thing that we provide in this formulation is we give you the flexibility to either use pick and choose from either classes of these transformations. So in insert, you could insert a print statement, assuming that prints are like dummy outputs and it doesn't change the functionality of the value that is being returned by this function. You can add some dead code. I have some comments on this, on like how you can bypass this to make sure that a compiler doesn't just throw out all this dead code. Or you could add some embellishments like try catches, which is just your way of adding extra code. So you could just add in this new line, and the task now is to, or you could like unroll loops. You could do all these little tricks which don't change the functionality and only slightly modify how a human perceives it. And the real question is, how do I select a set of transformations from this space of transformations so that I go ahead and manage to fool the classifiers that I have? And let me illustrate the difficulty of this problem through like a simple example. So let's say I have this little program and I'm allowed to change one variable name, one of these two variable names. And the way I would go about doing so is I pick site one. Let's say this is where I want to go ahead. This is the variable that I want to go ahead and change. Now I have like a vocabulary to pick from. So I know X should be replaced with something, and this is that list of something. I greedily try out each of these choices. Remember the setup. I insert these choices, push it into my model. I predict what the output is or the loss is. And I keep doing this until I find that particular token or that particular replacement which maximizes the loss. So we're trying to fool this model, so we're trying to maximize that loss. Similarly, you do this for the second site, and you pick a winning combination. So you pick a winning candidate. So greedily, you see whether the loss was great for R or Q. If it is for Q, you know that Q is the best possible thing that you can replace this variable with. But this game becomes a little complex if you start looking at multiple operations simultaneously. So let's assume foo1, foo2 are also replaceable, although this is like a function name. So assume these are user-defined function names which can actually be changed. The name can be changed. So under that assumption, let's say you have 4 choices over here, and let's say you have to pick any 2 of these. So let's say you have the luxury to perturb or pick any 2 of these. So immediately this blows up combinatorially. So this is an exponential problem. And what is worse is not only do you have like a multiplicity or like a combinatorial element in like picking which sites need to be transformed, but then for each of those sites, you also have this some sort of like a greedy approach of like figuring out what the best transformation is for those sites. So this is the difficulty of this problem. And what I'll discuss next is a formulation and an enhancement that we came up with, which gave us like a decent leg up in terms of performance. So yeah, so here's the formulation, the crux of the formulation. So what we do is, as was motivated in the example, we identify 2 variables to really go ahead and optimize. And this is also, I think we are to blame for a poor choice of these variables, but this is what we finally stuck with, and this is what's in the paper as well. So one variable we just call the Z, which is the site selection variable. So site selection really means Z is helping me pick which of these possible sites that I need to go ahead and transform. So it's just a bit vector or like a 0, 1 vector where high means I'm going to select that particular site to go ahead and transform. So I've just denoted that with a hole, and that hole will be replaced with some concrete value from this list of tokens that I have. And if it is 0, I'm just not going to touch it, and it's just going to remain as it is. So here's another example, 1, 1. So I change x in foo2 and I keep y in foo1 constant. Now, what this formulation does is it immediately makes it very convenient to define what an attacker's strength is. So now I can model how much power I can attribute to an attacker. So if an attacker has the luxury to modify every possible site in a program, this would just be an all ones vector. If it is just one site, it'll just be 1, and the rest would be 0. So that's like a nice, convenient way to model an attacker's strength. And the other variable is the other part of this whole story, which is after having chosen what site we need to perturb, we need to actually go ahead and fill those sites with some values. And this random variable u is what actually goes ahead and determines that value. So we have like a vector of, this is like a one-hot encoding signifying one of these values. They're all randomly initialized. And through the optimization process, they get filled up with one of these values such that this constraint and this formulation is satisfied. So the formulation really is, and this is like the crux of the work, is we define a perturb program as simply z times u. So if you have 1 in z, that means you're going to pick the transformed token instead of the original token. And if it is 0, which is 1 minus z being 1, you pick the original token. So this is your resultant program. So with the additional constraints that the summation of z should be less than k, so that is the attacker strength. So k is defined a priori based on your threat model, and sigma ui being 1 is just to signify that this is a one-hot encoded vector, which denotes one of the variables from this set and not multiple variables. So that's the core of this formulation. And remember, this was our setup where we have a program and we have a trained model. And instead of passing in this program, we pass in this perturb program. And through a first order sort of gradient method, we optimize for these two random variables. So that's the overall formulation and the setup that we had. And we had two ways to go ahead and solve this.
So one question.
Yeah.
So in this formulation, you can't like insert new lines, for example. Is that right?
No, you can. So one of the transformations that we had, I mean, so it needs to be massaged. So you're right. I mean, it'll. I would need to have some padding over here, and that needs to be managed. It's a little bit of like a more of an implementation detail. But as such, the formulation itself incorporates both the insert kind of transformations and the replace kinds of transformations. So yes, this resulting program can have the length of this token. I mean, this resulting program can be greater or lesser than this original program.
Thanks.
Yeah, nice. Right. So this is the formulation, and yeah. So we had two ways to go ahead and solve for this. So we used. One is we used like a joint optimization method where we solve for both these random variables at the same time jointly. And in another variant, we tried the alternate optimization method where we hold one constant, optimize the other, and then we hold the other constant and optimize the first one. So we tried both these out to see which of those would provide us better results. So yeah, we evaluated this on two large data sets. So one on Python and one on Java. We evaluated this on two models. So one is the seek-to-seek model and one is a code-to-seek model. So code-to-seek is considered the state-of-the-art in this space where they've compared this to transformers and all the other state-of-the-art NLP language models. So code-to-seek is what performs well. Its input is slightly different. I can talk about it probably later as to the nuances between these two models. And we tried it out for two different classes of transformations, 5 replace transformations and 2 insert transformations. And the metric that we used to evaluate was the attack success rate. So for every sample that was previously correctly classified, how many samples are now or incorrectly classified as a consequence of these transformations. So that's the metric that we're trying to measure. So let me just make sure that everybody gets on board and on reading this results table. So no attack is, of course, we don't optimize any of these variables. So p perturb equal to p, no change. The attack success rate is 0. For a random attack, which means that I randomly pick one site. So I'm not really optimizing this. I'm randomly picking one site in the program, and I'm randomly replacing that one chosen site with a token from my vocabulary. So that is my attack, or inserting a token from my vocabulary. One of those. I'll just use replace for the purpose of this conversation. And what we find is the attack success rate remains to be 0. It's 0.0 something. So it's as good as 0, which just shows that blindly trying to make changes in this program will unlikely yield any interesting results. Following the same line of thought, we compared ourselves to another work which was again released around the same time that we were submitting this work to ICLR. I'll just call them, they're a group from the University of Wisconsin. And what they try is, in fact, they don't have any of the formulation that we propose, but instead they just randomly pick one site in the program and then optimally go ahead and find the best replacement for that chosen site. So in order to be fair, we made sure that we use the same optimal algorithm that they use, but in the context of our formulation. And what they find is they had like an attack success rate of around 20. So 20% of codes which were previously classified correctly were now being incorrectly classified as a consequence of making this perturbation. These are our results of the alternating optimization and the joint optimization approaches. And we see a modest gain, although this immediately signifies that sites itself have a decent amount of information in them. So it's not enough to randomly pick a site, but it is probably important to choose which site you're going to perturb and going to transform. So this is these are the results that we saw for the two variations of our the two approaches that we use to solve our formulation. Modest. So, and this is what happens in the case of 5 sites. So all this was like one random site being picked in the program. For 5 random sites or like 5 optimal sites, this is the attacker's strength. The gain starts increasing, which again is more evidence that it's probably important where you're going ahead and perturbing. So this is like a 6% increase in your success rate. So during these experiments, what we also noticed was the loss, and I can go into some detail about this as to what exactly this captures, but across the iterations of the alternate optimization and the joint optimization routines that we were running, we saw like a very spiky loss signature. And that made us suspect that probably the loss landscape itself is fairly spiky and fairly irregular. And what we did was we just used a neat little sort of smoothing trick where for one of the random variables, we just add like Gaussian noise in order to just smoothen it. And with the hope that the smoothing function is easier to sort of walk through and it's easier to optimize. Yeah, sorry, was there a question? All right, all good. So this is the modification to the formulation that we did. We could have added this noise to both the variables. We just do it for one variable because computationally this can become quite expensive of adding this noise and evaluating the loss at different points. So what we did find was this is randomly sampled token from some program in our test set where we find that, okay, this is the effect that the smoothing adds to the entire picture. So you see that these are spiky losses which become smooth. And I'll also walk you through some examples of where this effect is manifested. And what we find is with the randomized smoothing, the best result, which is alternate optimization, we see a jump of like 14% ASR for these 5 sites and roughly around 10% for like a single site. So that's an interesting result that we had, where we saw that, okay, with just one site being exposed to us to go ahead and perturb, we were able to get like a 30% dip in the original success rate. So, and 50% for 5 sites. So that is kind of concerning. I would be concerned for sure. So the next thing that we evaluated was whether training this model adversarially, making them robust against this formulation, had any advantage. So the results that we saw, this is from the previous slides. For no adversarial training, the attack success rate was somewhere around 20. With our alternate optimization method, there was a jump of around 3 points, and with the randomized smoothing, there was a jump of around 10 points for one site. And what we see is, if we train this adversarially against formulation of the Wisconsin group, things do improve. So you see that immediately from the attack success rate from 30 dips to 20, and the alternate optimization is also hovering around 20. And what we see is, with our formulation, this pretty much comes down to somewhere around 10, like 12%, 13%, with our best formulation, even attacking using our best formulation. So this was the key set of results that we had in this work. Here are some examples. So this is like an unperturbed program, and it is trying to predict this function name. So this function name isn't really provided during test time or during training. So what it is trying to predict is this function is trying to set some item. And you see that it unperturbed, it predicts it correctly. With the University of Wisconsin formulation, what they recommend is going ahead and modifying this particular variable name called name to virtual name. And as a consequence, nothing really happens. So it's not good enough for perturbation to go ahead and modify it. And with our formulation, with the optimal site selection, not a random site selection, and this optimal site perturbation, we see that it's a different variable name. Although note that both the variable names are the same. It's just that we don't deal with the textual properties as such, and we are looking at the syntax trees and dealing with the slightly more nuanced representation of these programs. So we immediately see that our method is recommending changing this particular name. So these two variables are going to be changed. And what it is recommending is it's asking us to change this to QI SRC. And as soon as I change this, the prediction becomes right, and it no longer is set item. Here's another extreme example where even our formulation fails. So for this particular function, the Wisconsin group's formulation recommends changing this particular loop counter. So instead of key, make it save. Doesn't have any effect. Our variable instead asks us to change the function argument from A to copies. Again, still no effect. But then with randomized smoothing, it says, okay, stick with the site that you discovered, but then change it to date time instead. And what we see is the label gets flipped. That's pretty much it. This is the crux of what I wanted to convey. So in conclusion, what we have presented in this work is a principled approach to even think about this problem of how does one go about adversarially perturbing programs. So we lay out this nice little formulation where it's agnostic to the model and the kinds of tasks that you have in mind. And this is like a wake-up call for folks who are keen on pushing out these kinds of ML models in production. So one needs to be really careful about the consequences of these kinds of attacks. And the aim is to hopefully use this work to motivate what's the best way to design these representations and design models, which can probably match human understanding of how we go ahead and comprehend these programs. And that's the exciting sort of cognitive aspect of behavioral experiments, to probably inform the kinds of models that we learn in this space. So, yep, that's pretty much all that I had to convey today. Thank you. Happy to take questions.
I have a question.
Sure.
So I have a question about using the noise to smooth out the So that noise, so the U actually are the token embeddings, right?
I'm sorry, I didn't hear your last part.
So you have Z and U. So the
That's right.
U's are the token embeddings, right?
So the U's are not really token embedding. So the U's are they're just random variables which are learning not the token embedding, but just a one-hot representation for which token to pick. So this is not the token embedding, which is from some pre-trained model or anything of that sort. This is just a randomly initialized vector, which is being molded through the optimization process to take the shape of like a one-hot encoded vector, where the one signifies the specific token that we're going to pick from this particular set.
Okay, so actually, which one do you actually pick is actually denoted
Exactly.
by the Z.
Exactly.
Okay.
Exactly.
So yeah, I'm just curious about what is actually the intuition behind it. I mean, why adding the noise would be able to smooth out the optimization, and particularly the loss.
So I think this has definitely been seen in like previous works as well in the optimization literature of why smoothing plays a role. But what's a good way to express intuition for? So in some sense, you're just trying to average out the multiple values that come up. So so in this formulation, when you're adding this noise, in some sense, you're sorry, where is the noise? So let me show you that. So what this is doing is, instead of sampling from one particular point, you're just sampling from you're getting a more robust estimate of that point given the surrounding as well. So if in case you're on some particular peak or trough, this just ensures that you're taking an average value across that landscape and not being completely biased by one particular spike that you may be sitting on. So that's essentially the intuition behind adding this kind of a noise. So you're just averaging out the effect of your neighbors in the landscape that you look at.
Okay.
Hi, thanks for a great talk.
Sure.
Do you have a sense for whether these adversarial examples generalize across models?
Generalize across models. The model performances, I'm not sure. That's something that probably we should go back and check. I don't think we checked this specifically, but I'm quite positive that they should be. Again, I mean, these are all hunches. The right answer is I don't know. I should go back and check. But what's been shown is, at least for this particular task, both seek-to-seek and code-to-seek behave they have pretty much similar performances, although they're architecturally fairly different in the kinds of inputs that they accept as representations and so on. So I'm not sure. That's an interesting question. I should definitely.
And the motivation for this was like there's some recent cool work in NLP where people have found that you can like train a translation model from examples from Google Translate and find adversarial examples on the trained model, stolen model, and then it generalizes sort of to Google Translate. And they've shown this sort of across different architectures as well.
I see.
It's not like super good, but it sort of works, which maybe it's these data manifolds are somewhat model specific, but more general as well.
Sure. That's interesting. I remember definitely a bunch of us when we were walking through this work. We had discussed using like a surrogate model as in exactly the same way that you described. But I'm not sure. That's definitely an interesting. But the hope is that if these models do learn code agnostic, I mean, code general properties like structure and semantics, and then quite arguably it should transfer. But yeah, it's definitely an interesting investigation.
Thanks for the great talk. I had a quick question about, is there any sense of how this works against, for example, like the code clone algorithms in the literature?
Yeah. So code clone, so it hasn't, I'm not sure whether code clone is a task that has been evaluated on code-to-seek. So we were trying to at least restrict ourselves to the benchmarks that most of these prior works have used. But so is your question saying, will this algorithm be applicable in the code clone context, and my thoughts on like how effective it would be in trying to fool a code clone detector?
Yeah, just your overall sense if there's already been work comparing this kind of approach with like maybe a code clone algorithm that would determine if it's a clone of merge or not, or something.
I'm unsure, because code clone is like a tricky task where the crux of these code clone detectors is to detect these kinds of obfuscation operations that we define in this work. So I can see like a conflict between the objective of code cloning and code clone detection and these kinds of operations. But that said, I'm not sure. I'll have to give this some more thought, but there are definitely nuances that I foresee, which makes it really non-obvious of like what's the right way to frame this in that context. And the formulation, of course, would work, but it'll be interesting to see whether the application itself would benefit from this kind of like an attack strategy.
Okay, thanks.
Does anyone else have any final questions? All right. Thank you again for giving the talk.
Thank you. Thank you so much, Luke. Thanks for having me over.
Thanks, Shah.
Yeah. Thanks.
Thank you.
Thanks, David.
Great talk.
Thank you, Sergio. See you everyone.